about more than half an hour, 35 minutes, and then almost a bit of earlier lunch. So.
All right, thank you. Thank you, everyone, for coming to the talk, and thank you to the organizers, I guess. But thank you for inviting me and putting this program. OK, so I'm going to talk about ordered Ruzsa-Szemeredi graphs and fully dynamic matching. This is basically the second part of the talk by Sohail and Alma unofficially. Okay, I mean, Sohail told me to talk about these things, so I will talk about them. And a question I want to ask, which I don't want to ask directly, so I'll ask it this way. How many of you know ordered RS graph? How many of you have heard of this term? OK, good. So I may have to repeat some of the things Sohail and Alma talked about, but I try to skip over them fast. OK, good. And this is joint work with Sanjeev Khanna and Peter Kiss. So quick reminder, matching is a collection of vertex disjoint edges. And for instance, this is a matching in the graph. And in the maximum matching problem, we want to find a matching with the largest number of edges. And as a notation, n is going to be number of vertices, m is going to be number of edges, and mu of g is going to be maximum matching size in the graph G. Okay, so this is my notation. We are talking about fully dynamic matching problem. We have a graph G that undergoes insertion and deletion of edges. Okay, and the goal is to maintain a large matching and approximate maximum matching in G after each update. You want to maintain the edges. Basically, you have to be able to report every edge in order one time. And generally, when you're talking about dynamic algorithms, the goal is to beat the naive recomputation. What you can do is that after each update, you can just go ahead and solve the problem from scratch. You want to do something which is better than that. And we are going to focus on finding a 1 minus epsilon approximation for some fixed epsilon. It's going to be important that for us, epsilon is not going to be like it's not really a function of n. Okay, it's like as small of a constant as you want, but is independent of n. Okay, and really the motivation question is that can we beat this naive order n update time? I'm going to it may not be clear how you can even get order n update time. It's not entirely trivial, but you can do it, and let's say that's the benchmark of getting order n update time that we know how to do, and it's easy. It's a very good exercise, like an undergrad algorithm level exercise. The question is if we can do better than that. Okay, good. So what do we know? You can say we can do better than order n if you are sticking to the definition of order, really. So if you want a small O of n, then we know you can shave off this big improvement of log star n. Actually, not even log star n, some polynomial in log star n, to the 1/6 or 10 or something. So basically, this was this work with Sanjeev, Sohail, and Huang, and that we showed that you can do better than n. Okay. Then there's this very nice recent result by Yang Liu that shows you can actually get n divided by 2 to the square root log n. So you can do something better than n to the 1 minus a small, or sorry, you can do n to the 1 minus a small of 1 update time. Okay. And this result actually hits a barrier based on online matrix vector multiplication conjecture. So this is really the limit of that bound. Okay, so this is what we know. So you can say, yes, we made some progress on this question. But realistically, we don't know much still. Okay, if we wanted to beat this factor n by a respectable polynomial or something, we really don't know how to do it. And it's not like we don't know it's hard. We don't know whether it is hard. We don't know anything. We don't have a lower bound that says it is hard. We don't have an algorithm. We just don't know anything. Okay, cool. So this is where we are. Now, there was this very recent exciting progress by Sohail and Alma that come up with an algorithm like this. So they gave a randomized 1 minus epsilon approximation algorithm that I like to say potentially uses a square root n time. Okay, and the question, so this is the result. You can get 1 minus epsilon approximation and have update time that, again, I want to say, quote unquote, potentially is a square root n. Okay, but what does potentially mean? Okay, potentially here is that the runtime of their algorithm is stated in terms of some graph theoretic notion. In fact, the runtime or the update time of their algorithm is a square root of n times some parameter that for now I'll just call it ORS. It's a function of n and epsilon. It's a well-defined mathematical function. It's on some extremal graph theory. For now, let's stick with this. Some of you have heard of what is ORS. We'll get to it. I will define it shortly, but for now, it's this. Okay. So this is the bound they'll get. Okay. And at this point, what we really know is that we don't have a good understanding of ORS itself. We just know that it is at least some n to the small of 1, basically n to the 1 over log n. And we know that it is upper bounded by some n divided by some log star n type function. Okay. So what is happening is that if it so happens that ORS is actually closer to the lower bounds, okay, then we have an amazing algorithm. We have a square root n. We beat that factor n that we had no idea what to do about it, but like a square root n factor. Okay, good. If it so happens that the ORS is closer to this side, then we may not get anything from this algorithm. We will get some other things in some other result, etc. We'll get some better lower bound somewhere else. Okay, but this is the result. Okay. Sounds good? Okay. And one thing I wanted to say is that you can state this result for all values of epsilon, but when epsilon becomes some sub-constant, especially when it hits around 2 to the minus root log n, or in fact before that, then we know ORS is omega n. Okay. So this algorithm is really focusing on the case when epsilon is some constant and not too small. Okay. And I'm saying this to contrast this with a bunch of work that focus on epsilon being some polynomially small quantity. Okay. From sublinear algorithm point of view, I would think that a small epsilon, like a small constant epsilon, might be the more relevant regime that we want to focus on. And this is what this works focus. And the same way my talk is going to be about that regime. Sounds good? Okay. Now let me just tell you our result compared to this bound. Our result is basically, we looked at this bound that Sohail and Alma achieved, and we wanted to try to improve it a bit further. In fact, it started with just understanding what they're doing, really. Okay? And it turns out you can improve this bound further. You can basically get an algorithm that runs roughly ORS time, n to the small of 1 times ORS, okay? And achieve a 1 minus epsilon approximation. And now, again, if you use this language of potentially, this algorithm potentially can be as fast as n to the small of 1 if it so happens that the ORS is as small as what we can prove currently. Okay, sounds good? So if we live in a world that the ORS quantity is n to the small of 1, then we suddenly get a super fast algorithm for matching. We beat this factor n, like n to the small of 1. We are more or less done with this problem, up to what is n to the small of 1. Yes?
Than the previous one?
Good question. Modulo this one, yeah, so ORS is upper bounded by n. Okay, so modulo this is small of 1 differences or things.
The same with of 1 in the exponent?
No, they're not the same. Okay, and these epsilon dependencies might be a bit different between them. And so it's not entirely clear if this is always better than that, but up to n to the small of 1, it is always better.
So you see, we don't know anything about ORS except that it's somewhere between n to the liter of 1 and. What are the beliefs?
I don't know. I'm happy with either extreme. Like anything in the middle, I'm very happy with. No, but conceptually, think of this also some sort of a barrier. Basically, this is saying this is the complexity of the problem. This is characterized by this ORS. I mean, this is not a characterization. We don't prove a lower bound also, but at least it shows that if you want to prove a lower bound, you either condition on ORS also, or you are using ORS graph somewhere in your lower bound, or you are changing the existing bounds about ORS, for instance. Okay. I don't think, yeah, and I will talk about that even without knowing this thing, this algorithm is quite useful, even if we don't know what is ORS currently, okay, in a practical setting. But I'll get to that a bit later. Any other question? All right, so now let me try to unpack this result. What is even ORS and things like that? And I'll try to go over them fast. So ORS comes from these Ruzsa-Szemeredi graphs. It's an extension of these graphs. A quick reminder, an induced matching is a matching in a graph such that there are no other edges between its endpoint. So the induced subgraph on the matching is just a matching. And R by T RS graph is a graph that has T induced matching, each of size R. Okay. So this is a 3 by 4 RS graph. Okay. So this is one induced matching of size 3. This is 3, 3, 3. Okay. Good. Yeah, there are 4 of them. This is payback for those of you who missed Sohail's talk. But yeah. All right. Okay. But this is 3 by 4. Okay. Good. So this is the RS graph. And we are generally interested in RS graphs that have large values of R and T. In this talk, we want R to be asymptotically equal to N. Okay, this is like theta of N, N over 1,000, N over million, but theta N, we know what is theta N. Good. Okay, so these are RS graphs. Now, Sohail and Alma defined this ordered RS graph. The same setting, really, R and T, etc. Everything the same, except that these matchings are now ordered. Okay, the set of matchings are an ordered set. You have M1 to MT. I will define them in the opposite direction. That's what I'll define. So here, MI is induced among the edges from MI to MT. So when you want to talk about the inducedness of MI, you will ignore the edges of matchings that appear before MI. So these matchings are not induced in the entire graph, but induced from MI to in the superscript. Anyway, so this is M2, for instance. If you have a matching like this, you are allowed to have an edge like this from M1. This is not induced in the entire graph, but when you're talking about M2, you ignore edges of the matchings that appear behind it. Okay, so this is okay. This is still an ORS graph. But you cannot change the name of M1 and M2, okay? If these edges are M1, then this is no longer an ORS graph. Sounds good? Okay. So that's the definition of the ORS. What is the state of the art? Let me define this quantity. ORS of N and alpha is the largest number of these matchings T that you can get if you require the size of the induced matchings to be alpha times N, okay? So we will later set alpha to be epsilon or some function of epsilon, okay, which is a constant. And we want to say how many such matchings we can in our graph. We can pack inside the graph. So does this definition make sense? This is very similar to the definition for RS. Now we just apply it to ORS. Okay. And here, this is basically the state of the art. On one end, we know constructions by many people in this audience, actually, that shows ORS and RS graph themselves require to have n to the 1 over log n induced matchings. Okay, this holds for any alpha less than 1 over 4. Okay, good. And on the other hand, we also know this upper bound by Sohail and Alma based on the prior work that shows you can shave off like log, iterated log based on this parameter alpha. Okay, so you see this is effective, this is very close to n, okay, just not exactly n. And this other part is very close to n to the small of 1. It's not even a polynomial in n, okay? And this is the gap we know about this quantity. This is the state of the art. And you might think that, okay, ORS graphs are defined recently. Maybe we don't know much about them. But even for RS graph, this is effectively what we know, okay? So even for closely related concepts like RS graph that have been studied a lot in the last many years, modulo what is this dependency here, this is all we know about RS graphs as well. Okay. Sounds good? Okay. So now the connection, this is the part that I'm going to skip basically. I'm just going to mention that basically Sohail went through this thing of they come up with this notion of ORS graphs because they form a very natural barrier for our current knowledge of how to solve dynamic matching problem. What I'm saying, this is not a formal lower bound. It's not even conditional or anything. We don't have such lower bounds. But more or less, it seems like going below this ORS of n and epsilon seems to be something that we don't know. We have no idea how to do that. So we don't know any dynamic matching algorithm that can get an update time that goes below this runtime. Okay, this was the barrier that Sohail talked about. Okay. This barrier is somewhat related to OMV conjecture. OMV is also about finding induced matchings inside a matrix, although the parameters do not match really. It's similar to OMV if you set epsilon to be some 1 over some polynomial, okay? Which we know in that case ORS is a very large number. Okay? And in fact, a similar type of argument also appears in this work of Yang Liu that prove lower bounds for approximating matching in dynamic setting when epsilon is some polynomial in N. Okay? So finding this induced matching in a graph seems to be a hard task. It seems reasonable to believe that ORS is a good candidate, is a good yardstick that we want to achieve such bounds. Okay? We want to get update times close to ORS. And again, I think Sohail covered this more, so I will skip talking about why this is a barrier. Sounds good? Okay. But even if we go with this barrier, now we can state result of this BG24 paper. The runtime is basically root of n times ORS of n and f of epsilon. It's not exactly epsilon. It's some function that changes whether your graph is bipartite, non-bipartite, and things like that. But some f of epsilon. Okay. And here you see this bound has roughly a square root of n over ORS gap, even with this new barrier that we were aiming to achieve. And this gap is non-existent if ORS itself is close to n, then this result is n. But in that case, this doesn't give us a good bound. Okay. But in the regime that we are super interested in, this result is when ORS is n to the smaller of 1. So then there is a square root n gap, basically, between this algorithm and this barrier that like Sohail and Alma were talking about. And that's where our result comes in. Our result basically is just closing this gap. Okay, we are saying that this barrier that these guys found is really, like, we can just get to that bound, basically. Okay? So we can get an algorithm that have runtime of n to the small of 1 times ORS of n and f of epsilon. Okay? And in some sense, this means that maybe that barrier of the fact that we don't know how to solve ORS graph can be the only barrier we have for solving matching. Okay? If it turns out the ORS graph are sparse, so that barrier doesn't exist, then we already have a fast algorithm. Okay? And maybe if we can just sit down and think about how we can solve this hard type of inputs that Sohail talked about, then we'll get an algorithm for dynamic matching also. That's really the only thing that is left, quote unquote, for this problem. Sounds good? All right, now let me talk a bit about one feature here, which is related to what Clement was asking before. This algorithm doesn't need to know the value of ORS. This is already an algorithm. Like, as in it's not a non-uniform algorithm or doesn't need to get ORS as some advice. We don't know what is this value. The algorithm doesn't need to know it also. It just works. You can just run it currently. Okay. So it completely reduces this fully dynamic matching problem to a purely combinatorial problem. You can just go sit down and prove an upper bound on density of ORS graphs, okay? And then you will be done, okay? You'll get a fast algorithm for matching. It's not going to be easy, I imagine, proving upper bound for ORS for the same reason it's not easy to prove upper bounds for ORS graphs, okay? But now this is just this purely combinatorial question that we need to solve. One other thing, it's a bit cheesy, but let me say it's kind of a win-win situation at this point. Like, you can run this algorithm, quote unquote, in practice. I think Sohail mentioned the same thing also. Either this algorithm is fast, so we are happy with it. If it's not, it will find a dense ORS graph. Okay, so one way or other, we'll get something good out of this. All right, but actually, this part joking aside, this means that really the only hard instances that may appear in practice for this algorithm does not work should be very pathological instances that create something that look like an ORS graph. Okay. All right. So now let me talk more about our techniques. Okay. So first, I want to mention 3 background tools that it will be good to know even if you're not working on dynamic matching or if you want to later work on. These will change the problem significantly, and they're all standard at this point. One is that it's without loss of generality to assume the matching size in the graph is omega n. There are some vertex sparsification approaches that have been developed over the years. We can just apply them, and from now on, assume matching size is omega n. Then we have this result by Sohail that allows us to, at any point in time, we can get a 2 approximation to the matching size inside our graph in O tilde n time. Okay, so this is super fast. At any point, I can just stop and say, what is the size of matching in my graph? And in O tilde n time, we can solve. Finally, there are these boosting frameworks that basically reduce solving a 1 minus epsilon approximation of matching to this problem that gives you a set of vertices and asks you to find a constant factor approximation in the induced subgraph of those vertices. After that, it looks at that your answer and give you another set and another set. Okay? And this started by work of Andrew also, and then there were lots of follow-up work based on multiplicative weight, other techniques that give you this type of results. Okay? And this is where F is going to be very different, whether it is bipartite, general graph, and things like that. Okay. One thing I want to say, all these 3 tools have been studied in the context of actually streaming and sublinear time algorithm team of this workshop, and now they find application in many different ways. Okay. The corollary of these tools is it reduces the matching problem to something very concrete, which has been used in a bunch of other works as well. So let me define this problem. The problem is this. You start with an empty graph G. Okay. Then you are going to receive chunks of updates, okay? Roughly n updates at a time. So I'll give you n updates, okay? Then after each chunk of updates, I'll give you queries. A query is a set of vertices U, okay? You are guaranteed that there is a large matching inside U. There is an omega n size matching here. And the question is to return an order 1 approximate matching inside UI. So you can return another matching here. This is the problem, really. If you can solve this problem, you solve fully dynamic matching as well. Okay? This is a combination of the tools I mentioned. It's actually an easy combination of those tools. Okay? And the only important thing is that the update time you get for the matching problem will be the query time you have for this problem divided by n. Because you are processing every n update, you are running 1 query or like constantly many queries from this algorithm. Okay? So we want to get something with a query time which is a factor n larger than the update time we have in mind. And this parameter m that I was talking about, number of edges, refers to the maximum number of edges which will ever be present in this graph G. Okay, because now it goes under insertion and deletion. Okay. So what is the solution to this problem? We are going to give a family of algorithms, like A1, A2, etc. AK. It's somewhat recursive algorithm that have, I guess I should have said query time. They have better query time for this problem. Each of these algorithms is based on running multiple instances of the previous level algorithm there. And the base case of these algorithms is more or less really the same as the algorithm of Sohail and Alma. I think what happened is that we just put that algorithm in a different context, more or less. And once you formalize it in this other framework, it just suggests to you what you have to do after that. And going in, so basically, we are just repackaging that algorithm to a framework which maybe we understand better. And then after that, it becomes very clear how you have to improve that algorithm. Okay. And the base case is going to be their algorithm. Then we'll get better and better bounds eventually. The query time for this algorithm is going to look like this function. Okay. Let me unpack this. It has this n term. Remember that the query time is n times larger than the update time. So let's ignore that. Okay, we will get rid of that by dividing by n. Then it has a term like this. It's number of edges divided by n to the power 1 over k, roughly. Okay, so the more we go through this progressively better algorithm, this term becomes smaller and smaller. And this is, m is almost n squared. So this is n to the 1 over k. And the more we go through this sequence, it becomes smaller and smaller until it reaches n to the small of 1. And this is the opposite way. This is becoming larger and larger. The more we go through this sequence, it becomes closer and closer to RS. Okay? And this f of k is like you'll have to divide by 2 to the k or something. Sounds good? So this is the runtime of this algorithm. Good. So let me now tell you what is the algorithm. The high-level approach is like this. We had these chunks of updates. Now we are going to also pack a bunch of chunks together and call them a batch. Okay, so the algorithm processes a bunch of updates, like batches of chunks, and then restarts, forgets everything it knows, and restarts from beginning. So at the beginning of processing this batch, there is some graph G of old. This is the graph that up until now you have created. Okay. During this batch of updates, whenever you have an insertion, you add it to a new graph, this graph G batch. So all the updates go here. Okay. All the insertion. If there is a deletion that happens in the previous graph, you will remove it from there. But all your insertions, you pack them here. Then when you have a query was a set of vertices, you have to find a large matching. You see if you can answer it with inside this G batch graph that you are maintaining. It's a smaller graph, so it might be easier to answer here. So you try to answer it here. If it's possible, you're done. If not, I'm going to say that you're going to run an opportunistic sublinear time algorithm, and I'll define this soon. Okay. But basically, that's going to say that, OK, I couldn't find it here. Let me go and find it in G of old. Okay. This algorithm is like this. It tries to find a matching. Let's say it finds one. That matching exists. Okay, we are guaranteed that there is a large matching inside the graph. So if it's not here, it is there. It finds that matching. It removes the edges of matching to yet another graph that we are maintaining. It is this G of match graph. Okay, and then just continues as before. Now from now on, whenever I have a query, I'll first go here to answer, then I'll go here to answer, and if not, I'll go and run this opportunistic sublinear time algorithm to answer. Okay, good. What is this part? What is this sublinear time algorithm? So we would have ideally liked to have this algorithm. I give you a graph G with m edges. I give you a set U of vertices. You return an order 1 approximation in G of U. Okay. If we have this, and we want to do this faster than just reading this entire graph. Okay, of course, you can read all of G and solve it. You want to do this faster. If I could have done this, then you don't need to do any of these things I've said. This will just solve dynamic matching problem. But we know it's not possible. In fact, a couple of years ago with Sanjeev and you, we proved that you cannot get order 1 approximation to matching in less than n squared time. Okay, you have to read the input, okay, or omega m time. So we cannot do that. And the important thing is that these hard instances, the way it looks is that there are some small clicks at the top that are connected to all the vertices, and then there is this large induced matching here. Okay? I want you to have this picture in mind. These instances are only hard because there's this large induced matching here. And what Sohail and Almo come up with is that they came up with this algorithm that tries to be sublinear time, okay, in the following sense. If it can output a matching which is far from induced, so if it can output a matching which is very different from that hard instance, then it is going to run in sublinear time. Okay? But if it cannot find such matching, if your graph, for instance, doesn't have a large induced matching, then it is going to take as much time as needed. Okay? Basically, the runtime of the algorithm is roughly like this. It takes n to the 2 plus omega divided by d time. Okay? And d is the average degree of the graph on the vertices of this matching. If it's an induced matching, the average degree is 1. It's going to take n squared time. Okay? If it's a very dense subgraph, if it can find a matching in a dense subgraph, then it's not going to take too much time to find it. So it tries to be sublinear time. Sounds good? Our algorithm is going to be very similar to this. The only difference is that the runtime is going to be proportional to m number of edges in G instead of n squared. And one other minor thing is that it bounds even the maximum degree instead of average degree, okay, which makes it a bit easier to work with. But now here, let me go back. So I told you a bit about what is this algorithm that finds the matching there. How do we use it? One simple observation is that this graph that we create is a decremental graph. Okay? all your insertions are going here. There might be deletions there. You may be moving a matching out of it, but you will never add edges to G of alt. Okay? So this graph here is keep losing edges. Okay? Let me use that now, okay, to tell you why you can bound the runtime of the algorithm when it works there. And this is really the key idea that Sohail and Alma had, that basically, suppose you have removed a bunch of matchings M1, M2 to MK in a single batch. This is the time you spend on this graph G alt. Okay? Then by this sublinear type algorithm we had, this is the runtime it had. And this quantity, they are going to relate it to density of ORS graphs. How? More or less, I'm going to claim that summation 1 over d of mi can be upper bounded by density of ORS graphs. Okay. Looking at the audience, I'm not going to prove this. I will skip this part. This can be proven. Okay, good. So the only thing is that now let me just say what happens in our algorithm. You can bound the density of these edges that you remove based on density of ORS graph. And we do the same thing. The only difference is that now there will be m divided by d of mi. So this part, basically, the time you are spending on the ORS graph, the time you are spending working with this G of alt graph, okay, is m times ORS. Good. So what you have to do for processing a batch is to work with these graphs, okay, process multiple chunks of updates inside these graphs. And on top of that, in total, across all the updates, spend this much time on this G of alt graph. The time that you ever go back and check G of alt is, you don't spend too much time looking at that graph. You spend most of your time here.
That's a solution. Why do you maintain G match separately and not put it just in G batch?
I think mostly for analysis, really. I don't think there's a very crucial reason to change that. Yeah. So the only last thing I tell you is that how do we spend time here? Okay. In the base case, you effectively don't do anything there. Whenever you have to find a matching there, you just run a greedy algorithm to find it. Like you do the most trivial thing, just greedily go and find a matching. The number of edges there, you have these B batches. Each of them bring with themselves roughly n edges. So for instance, let's focus on G of batch. It has B times n edges. For B times, you are running a B times n edge. You are running a greedy algorithm over that, so it takes roughly B squared times n. So the total runtime of processing this entire batch is m times ORS, the time we spend on the old graph, plus B squared times n, the time we spend on these more recent graphs. If you pick the right value of B, this is going to give you n times a square root of m over n, a square root of ORS. Good? So, and this is the runtime we wanted, no? This is basically a square root of n times ORS. And that's effectively, this algorithm, it's basically just rephrasing of what Sohail and Alma did, okay? Now, in the last slide, I'll tell you just what we did. The only difference is in the first round, okay? Now that we framed the algorithm this way, when you want to solve the problem, you don't run greedy algorithm on G match and G of batch. You just recurse. You already have an algorithm that can handle these graphs. You run the previous version, like A of k minus 1 on those graphs, okay? What we know is that those graphs don't have too many edges. So when I write this by induction, instead of putting m here, I'm putting bk times n, the number of edges inside here. So I'm recursing on a sparser graph. Good. And if you do that, and then you parameterize everything, then the total runtime is going to look like the bound that we wanted. Sounds good? So the idea is that now you're recursing on a sparser graphs, and there's this big graph that you're not spending too much time. Okay? And conceptually, this is it. Then there is like the mess of figuring out what happens to the parameters between these graphs, how much you're losing in the matching when you recurse, and those things. Okay? But conceptually, this is it, really. Okay? And so I can put a QED here. Good. Okay. And this will be the runtime of the algorithm, okay? This query type algorithm. And then when you divide it by n, you get the update time, which is what we want. Okay, good. All right, so let me conclude. Our result is that there is a 1 minus epsilon approximation algorithm for fully dynamic matching with runtime, which is n to the small of 1 times ORS of n and f of epsilon, okay? So potentially, again, if we live in the world that ORS graphs are sparse, this algorithm is as fast as n to the small of 1. Otherwise, it might not be that fast. Okay, cool. Open questions. I think a nice question is that, is there any way that this barrier that Sohail talked about, and I mentioned briefly here, is there a way that we can formalize the further, some conditional lower bound based on OMV, or even maybe you make an assumption about OMV that is not necessarily equivalent to OMV, but seems a bit easier to work with, and then prove some lower bounds here. And if you do that, you also have to assume that ORS graphs are dense or something. So condition on ORS graphs being dense, condition on any fine-grained complexity lower bound you want, and then see if you can prove something here. Then this notion of these opportunistic sublinear time algorithms, in general, we use these type of things in different settings. Like sublinear algorithms are like crazily robust. Even when they do not work, they still work a lot, really. Okay, and this is one of those examples. There are lots of other places that you don't have to worry. Okay, you cannot find matching in sublinear time. You don't have to give up on that. Okay, or like Sohail's algorithm, we cannot find matching edges, but he can find matching size. And already that was a huge help to solve this problem, okay? So even if quote unquote weaker guarantees of sublinear algorithms can be super helpful. Then finally, this ORS graph, I mean, we talked a lot about it, but we really don't understand it. And will be good to understand it. I think a very good step is to relate it to ORS graphs itself. Okay, and Sohail and Alma actually mentioned that, is there a way to prove that ORS is also upper bounded by some function of ORS? And that's all I wanted to say. Thank you.
Are there any questions? So is it possible to use this type of techniques in other models, not dynamic algorithms?
Yeah. So last year with Sohail and Sanjeev and Juan, used something along, not along this line, but something motivated by RS graph to prove a streaming upper bounds, okay, and get n squared divided by log star and from upper bound side. I was interested, like after this, I thought a bit about it. If in a streaming one can do something, I don't know, like, but I'll imagine yes, really. I think there are like other places that one can look at, because RS graph lower bounds appear in lots of other settings as well, like communication complexity lower bounds, like distributed computing. So you might think also that, okay, the upper bound should also apply there.
Any other question?
I have one question, and that's, is this basically closed then? If I don't care about the n to the middle of one term, unless we improve the ORS bound, is it conceivable that someone does something completely different that doesn't depend on the ORS bound that you mentioned that would break these hard examples that you...
It will break a hard example, but these hard examples are not actual lower bound. Like if I give... And there are reasons, basically. If the type of way we use RS graphs to prove lower bound, usually assume that you know there is one fixed RS graph in the world, and you use that to prove the lower bound. Those type of things are not good enough to prove lower bounds for dynamic matching. So it is conceivable that there is an algorithm that can break through those instances and somewhat exploit the structure of RS graph. Like a question that is related to that is that if I... Like, for instance, this question, we don't know how to solve it. I give you a graph. I tell you it's an RS graph. Can you partition it into its induced matchings? We don't have efficient algorithms that do that, okay? But from the lower bound side, we never managed to exploit that. Okay, so there are these things I don't know, really.
I guess related to that question, what exactly is the dependence on epsilon?
So for bipartite graph, it will be epsilon to the -3. Okay. We lose epsilon factor for vertex sparsification and epsilon -2 for boosting. For general graphs, it will be 1 over epsilon to the 1 over epsilon. Okay. It is plausible that even for general graph, you can only lose poly 1 over epsilon. This is related to this poly 1 over epsilon pass streaming algorithm that I think these who are the authors? Fisher, Yara, and Sloboda. Yeah, good. Okay. So their algorithm is not exactly a boosting framework algorithm. I don't know if it can be phrased as boosting, but I'll imagine it doesn't sound too far-fetched. In that case, this can be poly 1 over epsilon even for non-bipartite. But even in the best case scenario, there is at least an epsilon factor gap there from the barrier.
So maybe it's a different question. Is it easy to figure out whether a given graph is RS or not?
Good question. I don't think so. No, if I give you a graph, can you check whether it is an RS graph? I don't think we know how to do. I actually, yeah, I don't know. Like you can, if I give you a graph and I ask you to find a large induced matching inside it, I think that's a hard question. That's NP hard. Yeah, but now you know that there are these things, so maybe you can find it. But I don't know an algorithm that can.
And this related, does this give you any better upper bounds in special, interesting special graph classes? Where you know more about ORS?
I don't. Okay. I don't know a dense graph class in general. Like what is a class of graphs that are dense and then do not contain RS graph as subgraph? So yeah, if you're working with a class of graphs that you can prove doesn't contain an ORS graph as a subgraph, yes, this immediately will give you better.
But none of these seems to be interesting.
No, it might be interesting. No, I think it's interesting. Like, what is an example of a dense graph class? The only one I know is this bounded neighborhood independence graphs. That's the only thing, which they, like even bipartite graphs do not fit that definition.
For random graphs?
Random graphs is good. So random graph, it's easy because they admit a matching cover. Based on like what Soil said, you can just sample. If you have a random graph and you subsample it to have n log n edges, it will have a matching cover. So you can have a matching cover for them, and then you can use that to answer. But I don't know what does it mean a dynamic graph is a random graph. You have to maintain the randomness throughout, also with the updates. No? So it might be a random graph plus some noise. And then you have to figure out how you're handling the noise.
Would expanders be able to use this?
Sparse expanders, no, because they're sparse. And dense expanders, I don't know. I don't think expanders do not give us matching cover, but
I don't think, from just the definition of expansion, I don't think it will immediately.
Do these things get any easier if you're just taking only deletions rather than fully dynamic?
Very good question. Yes. So there is a incremental, which only has insertion, and decremental setting, which only has deletion. In both of them, we know 1 plus epsilon approximation in n to the small of 1 time. I think in incremental, it's constant, and in decremental, it's like poly log n times functions of epsilon. So yeah, the problem is the combination of both.
Good. Then thanks again. And we'll continue at 2.